Alright, in the previous video, we have learned left-left condition, and we have learned how right rotation works in case of AVL tree over here. Now in this video, we are going to learn left-right condition. So let's say here again, we have an AVL tree like this, and we want to insert a new node to this AVL tree over here. So if we want to insert 25 over here, the first thing that we are going to do, we are going to compare 25 with the root node. Now in this case, in the root node, we have 70, and 25 is less than 70. So this means that we are going to continue to the left subtree. Now in the left child, we have 50. So one more time, we are going to compare 50 with 25. So we see that 25 is less than 50. It means that we are going to continue to the left subtree one more time. Now in the left child, we have 30. And here again, we are going to continue to the left subtree because 30 is greater than 25. Then we are continuing to the one more time left child. So we see that here 25 is greater than this 20 over here. So this means that we are going to add 25 as a right child over here. So after addition, we are going to check that if this node causes disbalance or not. So you know that we are checking only for the nodes in which we have children. So that's why we are going to start from 20. Now in this case, in case of 20, the left subtree's height is 0 and the right subtree's height is 1. So this means that the difference between them is 1. So this is balanced. Then we are going to continue to 30. Now in case of 30, we can easily see that the left subtree's height is 2 and the right subtree's height is 0. So this means that the difference between them is 2. So this means that this 30 over here is disbalanced. Now after finding the disbalanced node, we need to identify the condition. So as we said before, to identify the condition, we are going to find a path from this node over here, this balanced node, to the grandchild. Now to go to the grandchild of this node, which is 25 in this case, we are going to continue to the left subtree, which will be left. Then we are going to continue to the right subtree, which will be right. So in this case, we have identified that this is left-right condition. Now in case of left-right condition, as the name suggests, we are going to do first left rotation, then we are going to do right rotation. So first we are going to do left rotation, then we are going to do right rotation. So here an important moment is that we will do left rotation for the left child of this balanced node. So in this case, the left child of this balanced node is 20. So this means that left rotation will be done for this node over here. Now if we do the left rotation over here, it's obvious that 20 will come as a left child of 25 over here. So after rotation, it's going to be like this. So 20 becomes the left child of 25 and 25 becomes the parent of 20 over here. Now after finishing the left rotation over here, we are going to do right rotation for this balanced node. So in this case, this balanced node is 30. So we are going to do right rotation for this disbalanced node. So when we are doing right rotation, the disbalanced node becomes the right child of its left child, and left childs remain in this case same. So it's going to be like this. Root node comes down and the left child becomes a parent of root node, and this left child of this 25 remains in its place. Now here after rotation, if we check that if this node is balanced or not, we can easily see that it's balanced because the left subtree's height is 1 and the right subtree's height is 1. Difference between them is 1. So in this case, by doing this rotation, we have made our tree balanced. Now if you look at this left-right condition very carefully, we can easily see that first our tree was like this, which is disbalanced. So we can see that 30 was disbalanced. Then after left rotation, our tree becomes like this. So in this case, you can see that 30 remains as a disbalanced node here again, but here 20 and 25 changed its place. Then after doing right rotation, we can easily see that our tree becomes balanced. So in this case, at the end, our tree becomes balanced. So in case of AVL tree, whenever we are inserting a node and we see that this causes disbalance in the tree, first we are identifying the condition, then based on this condition, we are doing rotations over here to make our tree balanced. Now, as I mentioned, in case of left-right condition, first we are doing left rotation, then we are doing right rotation. So let's see how the algorithm of left rotation and right rotation looks like. So in this case, the first method is a pseudocode for the left rotation, and the second method is the pseudocode for the right rotation. So let's see how this is working in practice. So here, for example, let's say we have this balanced node like this. So we can easily see that this is left-right condition, because to go to the grandchild of this 30, first we are going left, then we are going right. So this means that this is this balanced node. So first we are going to do left rotation for this balanced node, then we are going to do right rotation. So to do the left rotation, as the algorithm says, first we need to create new root, and we are going to set this balanced right child to this new root over here. So in this case, as we said before, we are going to do left rotation for the left child of this disbalanced node. So we are not going to do left rotation for this child over here, for this node over here. We are doing left rotation for the left child of this disbalanced node. So this means that we are going to create new root based on this 10 node over here. So the new root will be the right child of this balanced node. So in this case, we are taking as a disbalanced node 10. So the right child of 10 is 20. So this means that new root will be 20. Then the next step is we are going to set this balanced right child to the disbalanced right child and left child. So in this case, we know that it's null. So this means that this balanced node will become like this, because in this case we have only right child, so we don't have left child over here. So this means that if we set it to null, it's going to be like this. Then after doing so, we are going to set new root node's left child to the disbalanced node. So in this case, new root node is 20 and the left child of 20 will be 10 in this case. So our new root will become like this. So after doing so, our disbalanced node will become like this. So here you can easily see that we have changed the places of 20 with 10 by using this algorithm over here. Now after doing left rotation, as we said before, we are going to do right rotation for this disbalanced node. So in this case, if I do the right rotation, the algorithm is like this. First we are creating one more time new root node and we are setting left child of this disbalanced node to the root node. So in this case, it means that the root node will be 20. And here 20 has a child, left child of 10. So we are not touching the child of 20 over here. So that's why our new root node will be like this. Then we are going to set disbalanced left child to the disbalanced left child's right child. So in this case, disbalanced left child will equal to disbalanced left child dot right child. So here you can see that disbalanced left child does not have right child. So this means that in this case, this balance will be 30. Because in this case, there is no right child for this node over here. That's why it's becoming null. So we are going to set left child to null. So it's going to become like this. Then at the end, we are going to set new root node's right child to this balanced node. Here you can see that in new root node we have left child, so we are going to set 30 as a right child of this new root over here. So after setting it, our root node becomes like this. So as you can see, after doing left rotation then right rotation, our disbalanced node becomes balanced. So with these two steps, in case of left-right condition, we are making this balanced node as balanced. So this is how left-right condition works in case of AVL tree. Now let's see what's the time and space complexity for these rotations over here. So if you look at these methods carefully, we can see that here we are not doing any time and space consuming operation. In the left rotation, we are just creating new root and updating the left and right child of these nodes over here, and similar operations are done in case of right rotation also, because here again we are creating new root and we are just updating the left and right children of these root nodes over here. So this means that these operations over here will take O1 time complexity and they will take O1 space complexity, because here we are not performing any time and space consuming operation. So in case of left-right condition, the left rotation and the right rotation takes O1 time and space complexity. Now with this we have come to the end of this lecture, so hopefully everything is clear about left-right condition in case of insertion a node in AVL tree. Now in the next lecture we are going to look at right-right condition. So see you in the next lecture.